so we're going to jump here now to talk about the double integrals, what those mean. Triple integrals, well, actually evaluating one is maybe not too bad. I think we would probably recognize that, yeah, now we've got three integrals there, and the order here in this case, dz, dy, dx, we know what that means. The z comes first, the y, and then the x. Yeah, and so same old, right? This, do the integral with respect to z first, hold the x and the y constant. So this would be integral 0 to 2, 0 to x. Z's constant, so that'd be 1/2 xy z squared, right? At least what we get there. And then then we evaluate that for z, so that would be xy times x plus y squared. Let's write it here. And then, of course, 0 for z would be 0. So, yeah, and so the next one we're doing with respect to y, so we are going to have to multiply that out, aren't we? So it's going to be 1/2. So that'd be x squared plus 2xy plus y squared. And yeah, so we're going to integrate with respect to y, so we still need all that multiplied in. So it gets, it gets kind of ugly sometimes. 1/2 xy inside there, so it'd be 1/2 x cubed y. And then 1/2 times 2xy would be just x squared y squared. And then 1/2 xy cubed. And so now we've got something there we can integrate with respect to y. Yeah, the x are constants, so that'd be 1/4 x cubed y squared. That'd be 1/3 x squared y cubed. A lot of it's just keeping up with which one you're exactly doing here. So we're doing the y, so it'd be y to the 4th, so it'd be 1/8 xy to the 4th. And that's from 0 to x. And so as you can see, it gets kind of fun here. So we plug in the x for the y, so it'd be x squared, so it'd be 1/4 x to the 5th. X cubed, so it'd be 1/3 x to the 5th. Oh, how about that? It just turns out to be all x to the 5th then. One nice thing about it, so we just combine all those. 4th, 1/3, something, 24ths. (17 24ths). So we got 0 to 2, 17 24ths, x to the 5th. And so we do the integral there, so that would be 17 over 24 times 6. So 17 over 144. X to the 6, so 0 to 2, what do we wind up with? 17 over 144 times 2 to the 6th gives me 68 over 9. Okay, so it does get kind of lengthy there, a little bit lengthy. But usually they're pretty nice on, we get polynomials or some trig functions of some sort. But all right, now, so once we get to the triple integral, we're good. Sometimes, though, we need to know what it is we're actually doing here, what this all means. Of course, what we're let's just start kind of with a simple one here. Say we're doing a triple integral over region B, and the reason sometimes they label it B is because let's just start with B is this. B is the region made up all the points x, y, z, where x is between A and B, y is between C and D, and z is between R and S. Okay. So, I don't know why they choose jump up to R and S, but that's what they do. All right. So, what we have here then is what is region B? If x is going between A and B, y is going between C and D, and then z is going between R and S, wouldn't that be a box? Yeah. Yeah. So here we're doing a triple integral over a box, three-dimensional box. And then we're doing that triple integral for a function x, y, z. And so as far as visualizing what that means, it's kind of tough because we're going into 4 dimensions here, 4th dimension for our function. And so, but what they focus on in this case is let's just change up the regions that we're integrating over and make it more general. Instead of a box, make it some other shape, 3-dimensional shape. So that's what we're going to focus on is that. Because if you think about it, the first integral we just did wasn't even, we weren't even talking about a box. It was because the limits of our integration were variables themselves. Yeah, had some variables in those. So, and the other thing to note here, so to evaluate this integral, we could go since we're just going A and B and C and D and R and S are just numbers, we could do whatever order we want, right? Let's say we just keep them in those order. Let's do A to B, C to D, R to S, which means, of course, we're doing the Z's first. So we're doing dz and then dy and then dx. And so, when we were just doing double integrals, there were 2 options. We could either do y's and then x's or x's then y's. How many particular orders do we have here? How many ways could we change this? You could do dz and then dx dy. Then you could do dy and then dx dz or dz dx. So there's 6, right? There'd be 6 different orders. So that's part of the issue here. trying to figure out which order might be the easiest, I guess, is so it just adds to it here. All right, but anyway, and in this case it wouldn't matter. Probably it would just depend on what your fx, the function with respect to x, y, and z is. Tell you which order you might want to go in. One way might be easier than the other. All right, but like I said, what we're going to focus on is this this region being something other than just a box, integrating over a more general region, triple integral over a more general region. And so the notation here, triple integral over region E, there's just going to be quite a few different possibilities of the book. And I will focus on type 1 region for E. And that's going to be where the E is the region between two functions of the Z, two functions of x and y, continuous functions of x and y. So what that means is this. Here's what E is going to look like for this type 1. It's x, y, z. And the x and y are elements of some two-dimensional region D. Okay. So ultimately we're going to three dimensions for E. So D is something down here, some shape of some sort. So it's something out of XY plane there. So that's where our XY's come from. And then Z is going to be between two continuous functions of that over that region D, and they call them the U's, U1 XY and U2 XY. And so what that means in the drawing here, in the graph, is Z is between those two, and so we've got Z going between some level here, and then another height Z at this one. Draw the back side here. So that's our region E, where this is defined by our U2 function, and then this is the U1 function. And so E is that region there. Okay. Not just a box. It can be many types of shapes. Okay. But that's type 1 because if you think about it, what could we do? Well, we could get our original D here, not in the XY plane, but in the XZ plane or the YZ plane, or different ways. And so, depending on what this is, that'll adjust your other one there. So anyway, lots of complications here, but this is the one I'm going to focus on for now. All right. So what does that mean then for our triple integral? How should we go about it if this is what we've got? Well, it turns out the best thing to do in this case is to first of all, since z is usually a function of the x and the y, in this case we're talking about, first of all evaluate with respect, do your integral with respect to z first. And so we're going to integrate the with respect to z first, so z goes between u1 and u2 in terms of x and y. So we're going to do that first. And then evaluate. One way you can say it is because you still have a choice for x and y, you could do the x's first, then the y's for the x's. So yeah, just integrate these the last two as a double integral over d, and then you can do your choice there. Call it dA, like we called it before. So if you've got a type 1 region, that's what you want to do, okay? All right. So here is an example of that. All right, so let's evaluate triple integral over e xy dv, where e equals the x, y, z's such that we've got this. Y is between 0 and 2. X is between 0 and y minus 1. And then the z's are between 0 and y minus x. So the set up the limits there based upon what we've got here, and what we notice is that the z is dependent on y and x, so z is a function of x and y. The x, the way we've got it set up, is it's in terms of y. So dz, dx, dy, right? So the order would be dz. And so we're going to do our xy function. The order is going to be dz, then dx, and then dy. So z is between 0 and y minus x. The y is between 0 and y minus 1. And then, yeah. All right. So, let's see. The good thing is we're doing with respect to z first, so there's not a z here. So it's just x, y, z. It'll be 0 to 2, 0 to y minus 1. X, y, z would be that, and then we're evaluating from 0 to y minus x, and so yeah, you're going to have x, y times y minus x. All right? Go ahead and multiply that out. Xy squared minus x squared y. Now we're integrating with respect to x, so that would be what? 1/2 x squared y squared minus 1/3 x cubed y, 0 to y minus 1. That goes in for x, so we've got 1/2 times y minus 1 squared times y squared. minus 1/3 times y minus 1 cubed y. We want to integrate that with respect to y, so yeah, a little multiplying is in order here. This would be y squared minus 2y plus 1 times y squared. We're going to have the integral of 0 to 2 of 1/2 times y to the 4th minus 2y cubed plus y squared. And then minus 1/3. You know what y minus 1 cubed is? That's going to be y cubed minus 3y squared plus 3y plus 1. You can check me on that, but that. So that's going to be minus 1/3 times y to the 4th minus 3y cubed plus 3y squared plus y. And we do have some like terms here, so let's see, what do we got? 1/2 y to the 4th minus 1/3 y to the 4th. I believe that's 1/6 y to the 4th. Then we have 1/2 times that, so we have y cubed minus plus y cubed. Hey, how about that? Oh, okay. For the y cubes, I get those to cancel out, don't I? Because that'll be a minus 1 y cubed, and that'll be a plus 1 y cubed. So those are just going to go out. All right, and then I have 1/2 y squared, and then that's going to be minus y squared. So negative 1/2 y squared. And then we'll have minus 1/3 y. But it didn't turn out to be too bad. So what is this? 1/30 y to the 5th minus 1/6 y to the 3rd minus 1/6 y squared. 0 to 2. So we have 32/30 minus 8/6 minus 4/6. Whatever that turns out to be. Negative 14/15. All right. Okay. All right. Huh? Okay. Not too bad.